Swayam Prabha. Digital India. Educated India.
The DC motor is very similar to the DC generator in the construction, and generators usually operate more than protected location, therefore the construction is generally the open type. But on the other hand, motors are being used in the rugged environment or a very wide areas of application, such as the like they have a industrial application in the different ambient conditions, so they are exposed to dust, moisture, fumes, vibration, or the mechanical damages that can happen. Thus the motors are required protective enclosures. In general, that is only small construction difference. Otherwise the working or the principle behind the current motors or DC motors and generators are the same. So let us talk about the motor principle. Okay. So when we talk about the motor principle, means how the torque is generated when we apply the electrical signal. So when a conductor is carrying current is put in the magnetic field. Okay, so let us have kind of so this is the rotor and it is the magnetic poles. So this is north pole, this is south pole, and this is the direction of field, north to south. Correct? North to south is the direction of field, and there is a conductor which is placed here. Okay, so when a conductor which is carrying a current, so this is a current which is being supplied by the DC voltage and carrying some current, and it is placed in the magnetic field. Therefore a force is produced on it, and the effect of placing a current carrying conductor on a magnetic field, which is shown here exactly, this will be having a force depending upon the left hand rule. Okay, and it is found that if the current is going the magnetic field is downward and the current is having a tendency to move it to the left hand side, so suppose it moves in this direction, so this is a direction of force and it is inside the slot. So what will happen, it will try to put a torque, so returning conductor will be on the other side, so it will just start rotating. Okay, so the direction of force is tangential to the rotor, which is here, and this will produce the force into this distance which is free to rotate. The torque will generate. So basically it is kind of this arrangement. So one force is here and another conductor here, so it will just get rotatory pull. So similarly the torque will be produced on all the motor conductors which is placed in the slots. So if you see, there are many number of conductors which are being put in the slots, so all will get tangential component of this force, and as a resultant it will just start rotating. So this is a torque. So this is how the current carrying conductor in a magnetic field produces force, and it causes the rotor to rotate because it is free to rotate. Okay, so this is the motor principle, so you can write it in your own words, and the only thing which you have to remember that when it is, suppose this shaft is connected to some mechanical load, so it will start rotating, so it will be basically utilizing to drive the mechanical load, and it is being supplied by the DC voltage. So when we talk about the back EMF, Okay, so if you remember, when we was driving the EMF equation in a generator, we said that back EMF is exactly same formula which are being derived for the DC generator. So there, if you recall, the EMF generated was NP phi Z. This is in RPM, so, or we can write it like small n. This is RPS by A. So this is the EMF equation. The formula is exactly the same for the motor. So this is known as, in the case of motor, this EMF generator is known as the back EMF, or is also known as the counter EMF, because it is produced against the polarity of the applied voltage. And symbol have the usual meaning, so we can just recall where n is the speed in RPS. If it is in RPM, then we can write it NP phi Z by 60A. That will become in RPM. Okay, and P is the number of poles, phi is the useful flux, Z is the total number of conductors, A is the number of parallel current path. And it depends upon what type of winding is being applied to the motor slots. So when it is a lap winding, then L is equal to P, and when it is a wave winding, then A is equal to 2. Sorry, okay, I'll just write down, in lap winding A is equal to P, in wave winding A is equal to 2. So this is the difference. So whenever, depending upon the, the DC machine, you can consider the value of A accordingly. So this is exactly the same as we have derived in the case of generator. So now let us understand the equivalent circuit of DC motor. Okay, so equivalent circuit of a DC motor armature. So when we are talking about the main conductor where the applied voltage is DC from the external supply, and it will run the so the armature of a DC motor can be represented by so consider this is armature, this is a DC machine. Okay, this DC machine is being fed by a DC input voltage, and it will take current as I. So this equivalent circuit of a motor can be represented by, when this will go to the brush, so there will be some drop in the brush, so there is some drop, then there will be drop in the armature conductor, and then there will be back EMF which will be opposite to the polarity of the applied voltage. It should be this form. So remaining voltage will generate as a back EMF E. So this is V applied, and the current goes as IA, armature current, brush voltage drop, armature resistance, and this is the polarity. So this is the equivalent circuit of a DC motor, which I have already discussed in the generator case. And here if you write the KVL, you'll get V is equal to E plus IA into RA plus the voltage drop across the brush. So this is how you use it for the, so when the brush voltage is not given, you can assume it to 0. If it is given, you have to consider it. If it is given per brush, then you have to multiply by 2, because you have positive and the negative DC terminal where the brush are connected. So there will be basically a pair of brushes. A single brush cannot be used. So the EMF is generated by this and it carries a current of IA. Okay, so this is the equivalent circuit of a DC motor. So in this case, whenever you are given an example to solve or find out the back EMF or the quotient depending parameters, then you can just use this KVL equation. So it is a simple single loop circuit. Now the second term which is being very important is the torque in a DC motor. So we'll just try to find out the torque of a DC motor. So when a DC motor is loaded either as a motor or a generator, so that DC machine basically will be, the rotor conductor will be carrying some current. Either it is feeding or generating the torque, or it is being supplied by a external DC supply, which is normally the case of a motor. So these conductors lie in the magnetic field of the air gap, and each conductor experiences a force. That's what resulted in the torque. So the conductor which is lying near the surface of a rotor are having a common radius at its center. So for example, if you have like this, you have a rotor, right? Then there are conductors in this slot. So the mean radius can be assumed, which is passing through the center, for the calculation of torque. So this is like radius of the rotor RR, and this is a tangential force. Okay, so this is tangential force and this is the mean radius. So this is just an assumption. So we assume that the motor is rotating at the constant speed, and we know that V is nothing but E plus IARA, by assuming the fact that there is no voltage drop across the brush because it's very less, 1 volt or 2 volt, and multiplying both sides by EA. So what we'll do, we'll multiply both sides by IA. So what we'll get, V into IA is nothing but E into IA plus IA square into RA. Okay, so VIA, it is nothing but the terminal characteristic parameter. So it is basically the power input applied or power applied, and this is the I square RA drop which is having in the armature conductor. What is this EIA? So this is very interesting term. EIA is the back EMF into the armature current. So this is the electrical equivalent of gross mechanical power. So this is electrical equivalent of gross mechanical power, and this minus the drop of brushes, contact, wear and tear, that resistance or loss, if you remove, then it will be useful mechanical power. So this is a gross power which is being represented in terms of electric quantity E into IA. Okay, so if from here, if you want to calculate the average electromagnetic torque which is being developed by the armature, then we can just write it down as mechanical power is nothing but the omega times of tau average, where is represented by average electromagnetic torque. Electromagnetic torque, and omega is the angular speed of rotation. Okay, angular speed of rotation. So omega is the angular speed of rotation and Pm is the mechanical power. So if we just substitute the values, so P mechanical power is nothing but E into Ia is nothing but tau average into omega, and omega we can write as 2 pi n. Okay, so Pm can be written as E into Ia is equal to tau average into 2 pi of n. So from here E, we can substitute the value of E. We know E is equal to n p phi z by a, where n is in rps. So substitute these values here, we'll get tau average as p z by 2 pi a times of Ia into phi. Okay, so this is the formula. So this is called the torque equation of a DC motor. This is known as torque equation, right? DC motor. So this is the torque equation of a DC motor. So from here you have we can clearly see that few very interesting observation. What are these observations? That the torque produced, the average torque is proportional to the product of phi into Ia, and proportionality constant if you write A times of Ia, where A is nothing but Pz by 2 pi A. So this is important thing. When we will be trying to find out the characteristic of a motor, then we'll be using this proportionality of torque. So when let us understand the type of DC motor and their characteristic. Okay, we'll quickly see the type of let us write type of DC motors. So if you remember, in the case of generator, DC generators, we have a series, shunt, and shunt, which is basically the compound machines. So one by one we'll be talking about the types. So let us consider the shunt wound or shunt motor. Okay, so shunt wound means, if you can see the construction, the field winding is in the form of a shunt which is parallel to the armature. So this is the armature of our DC motor, the main conductor, and you have a parallel field winding. Okay, so this is your shunt winding resistance, this is the Ia, this is I, the applied voltage is V, and this is the current which is If, or we can clearly shunt resistance ISH. Okay, So the input voltage in this case, sorry, the input current I is nothing but IA plus ISH. Okay, at this term point, if you apply the KCL, you will get this relationship, and where I is the input current, which is from the power supply. Okay, IA is the armature current, ISH is the shunt field current. So ISH is the shunt field current. If you want, you can write it as where I is input current, IA is armature current, and ISH is shunt field current. Okay, so this is the current equivalent of the current balancing thing, the input current, field current, and the armature current. Now if you see the voltage equation, we can clearly see that V applied is nothing but the ISH into RSH, because this is in parallel. So between these two terminals, the total voltage applied is equal to the voltage across the armature and the voltage across this field winding. So this is the applied voltage across the field winding, and also V is nothing but E plus IRA. E is the back EMF, IR is the voltage drop. So it is the voltage across this armature, assuming that there is no voltage drop across the brush. So that is the assumption. Now if you want to have a power equation in this shunt motor, so what will happen? Just multiply the voltage equation both sides by the current. Okay, so now let us write down the power equation. Okay, so VI is nothing but the input power. So what we'll do, we'll multiply this equation by I. So V into I is nothing but E into I plus IA square RA or what we'll do first, write in the other form. So what will write that total input power is equal to the mechanical power developed. Okay, so mechanical plus the losses. These losses will be in armature and field winding. So this V I will be the input power and mechanical power equal to PM, and then we have losses. Losses means in terms of I square RA plus ISH square RSH. These are the losses, and PM is the useful mechanical power, right? So it is basically the difference. So you can calculate from here, the PM is the mechanical power will be nothing but VI minus VISH minus IA square RA. So this is nothing but V into I minus ISH minus IA square RA. Okay, so this is VIA minus IA square RA, and it is nothing but V minus IA RA times of IA, and this is nothing but E. This is what we assumed earlier, right? So the mechanical power equivalent is E into IA. From here we have just seen, just playing with the parameters, right? So here you can see we have written the power input as V into I. So what about V into IA? What is this power? This power is the electrical power supplied to the armature. Electrical power supplied to the armature. You have to be careful while selecting these values. So if you really want to calculate the input power, then you have to take the input current. For armature power, since it is a shunt motor, we have to consider the armature current. Now let us see the construction of a series motor. So in case of series motor, if you see the construction, the field winding comes in series with the armature conductors. Okay, so this is the arrangement where the voltage applied is V and the current which is feed is I. So this is IS, RS, and this goes as IA. Armature resistance is RA and the back EMF generators is E. Okay, so now if you apply the the current thing, then I is nothing but IA or I as such. All currents are same because it is in the series. Now if we apply the this is the current equation. Now let's look at the voltage equation. What does the voltage equation say? It says that V is nothing but E plus I into all current is I into RS plus RA. The armature resistance and the field winding resistance, they comes in the series. Okay, so this is the voltage equation. So there you have to consider the total resistance which is coming in the loop, the total series resistance. So now if you see the power equation, so like earlier, we can total power input is nothing but the mechanical power which is being developed plus losses in the armature in the field. So the total input power is VI, which is nothing but the total mechanical power developed plus losses in the series winding and the armature winding. So series is current is same, so I square RS plus RA. Okay, and similarly PM, the mechanical power developed is nothing but the E into I, because I and IA are the same. So this is the mechanical power thing. So when we talk about the compound motor, we have to consider both the series and the parallel combination of different field windings, and it may be short shunt or long shunt like in the case of generator. So we can do the same thing for those machines, the compound machines basically. So before going to the characteristics, let us just recall the armature reaction in the DC motor. Okay, so before we go to the other part of characteristic, then first let us understand the armature reaction in a DC motor. So in case of a DC motor, the armature reaction, as usual, the effect of armature flux on the main flux. In case of a DC motor, the resultant flux is getting the strength at the leading pole and getting it weak at the trailing pole tips. So you have to remember. So let us write down this one. So in DC motor, the resultant flux gets added or strengthened at leading pole and weaker or weakens at the trailing pole tip. Okay, so this is the effect in the DC motor. But the armature reaction causing this disbalance of the field, it results in the sparking at the brushes due to the delay in commutation, as it was in the case of generator also. So interpoles are placed between the main poles in order to neutralize the effect of armature reaction and brushes in the region and minimizes the sparking of the brush. So we have basically the main poles. So these are the main poles. And you have a rotor in the center. So this is north, this is south, or if you're rotating this way, you can discuss in north or south. This is the rotor. So you have the interpoles which are connected here. Okay, so these are known as the interpole to neutralize the effect of armature reaction. So they are the extra added pole, and the polarity of these poles are such a way that they generate the remaining voltage. So if the voltage gets high, it will go to the opposite polarity, so it is balancing the disbalance due to the armature reaction. Okay, so okay, when we talk about the pole, I mean whether it will be a south pole or north pole. So motor interpoles have a polarity opposite to that of the following main pole in the direction of rotation. So suppose the motor is rotating in this direction, and after this, if it is north, so it has to be the opposite, so it will be south. Okay, so this is the main difference. And when it is used as a motor or generator, it will automatically change the polarity of the interpoles to maintain the similarity or the effect, or to neutralize the effect of armature reaction. So we need not to worry about this. The connections are made such a way that it automatically takes care of the polarity based upon the direction of the field. So now let us talk about the characteristic of shunt or separately excited DC motor. Okay, so these are the main characteristic of DC motors. We'll be considering one by one. Characteristics of DC motors. Okay, so in the case of a shunt, so considering the first case as shunt and separately excited. DC motor. Okay, so in this case, let us first go to the speed and armature current characteristic. Speed and armature current. So in a shunt motor, ISH is nothing but V by RSH. Okay, and V is constant, ISH also will be a constant. Okay, the voltage applied will be constant DC, which is fixed. Similarly, the ISH also will get fixed. It means field is, the flux is the constant at no load condition. So we assume here that flux is constant at no load. Okay, so flux decreases slightly due to the armature reaction, and the effect of armature reaction is neglected, then the flux will remain the same. So we can write that the speed will be proportional to the E by phi, and E is nothing but V minus IARA by phi. So the speed is basically the proportional to the V minus IA into RA, assuming phi as constant. Okay, so the equation shows that the speed will be a straight line when it is so if you draw the characteristic between the speed and the armature current IA, so ideally it will be a constant, but practically there will be small drop which is proportional to I into RA. Okay, this is known as the droop characteristic. Okay, this is the rated speed, this is armature current. Okay, so this is the characteristic. Without drop, and this is real, and this drop is I into RA, I mean proportional to IRA. So in general, speed is constant for a DC motor with respect to the armature current. Similarly, if you talk about the torque characteristic, now second characteristic would be torque armature current characteristic. Okay, now we have seen earlier the torque, which is basically the average torque, which is proportional to the product of phi into IA. Okay, and here in the shunt or separately excited DC motor, the field current is constant, which is V by IRSH. It means that flux is constant. So phi is basically constant, with the assumption that there is no armature reaction effect, but it will be slightly reduced if we consider the armature reaction, but still it will be constant. So the basically the average torque will be proportional to the current. So the torque characteristic average torque will be nothing but, it should ideally follow this, but normally it is little deviated. So this deviation we'll see is because of what reason. So this is the generated torque. Okay, the relationship between the various torque, if you want to see, so the net torque will be the difference of, what are these torques? So tau n is the net torque. or also known as the useful torque, whereas tau g is known as the gross or the total torque. Tau g is the gross minus this is due to the friction and wear and tear. So tau f is the frictional torque, which is causing the loss, and tau is W is wind is torque due to the air resistance. So here if you see, we'll be having a parallel characteristic which is very close to this, and it will just go this way. This is ideal, and then this will be the tau n, which is presented by this. So this is tau n, the characteristic between the torque and the armature current. Okay, now